Hi, everybody. My name is Tobi Ore, and I am a recent PhD graduate from West Virginia University, where my research focused on improving seismic interpretation and inversion using deep learning methods. And today I'm going to be giving a brief talk about an aspect of my research that was funded by GSA's Geophysics and Geodynamics division through the Alan Cox Student Research Award. And this talk basically is going to focus on improving data-driven seismic inversions. So solving seismic inverse problems involves the reconstruction of structures and properties of the subsurface from seismic data. And this is crucial, especially in the energy industry, as accurate imaging of subsurface helps in making informed decisions. And this seismic inversion is achieved through nonlinear optimization that is highly dependent on the quality of the initial model and also requires numerous iterations, which make them computationally demanding, especially in the present era of large, massive seismic data. And to address this, several data-driven approaches have been proposed that leverages the advancements of deep learning, building on its ability to learn nonlinear relationships and approximate any arbitrary function without being explicitly programmed. So I propose a novel framework called Inversion DDIM that leverages the generative capability of diffusion model by reformulating it for seismic inversion. And basically, diffusion models are inspired by non-equilibrium thermodynamics and are a category of latent variable models used for generative tasks. They work by gradually adding noise to an input, which is called the forward process, and using a neural network to predict the added noise in a reverse diffusion process. And in my workflow, the velocity, that's for training my workflow, the velocity is fed into an encoder that transforms it into a latent space where the diffusion gradually adds noise and uses a neural network to predict the added noise. And the seismic data is also transformed into a latent space using a special kind of neural network called the swing network. And on the figure here is called the feature extractor, which extracts the amplitude features from the seismic data and uses that as guidance of the reverse denoising process of the diffusion model. And through this process, the denoising model actually learns the semantic information in the velocity map and links this to the amplitude information of the seismic data so that on deployment, given any seismic pre-stack seismic data, we can actually make an informed velocity prediction, which is the goal of seismic inversion. So to demonstrate the performance of our workflow, I'm going to be using an open source dataset called the OpenFWI, which is provided by Los Alamos National Lab. And I want to point out that this dataset is synthetic and the velocity was generated by mathematical functions with the corresponding seismic data obtained through forward modeling. Here I am evaluating the performance of our model using three different metrics: the root mean square error, the mean absolute error, and also the structural similarity. And these results are compared with two state-of-the-art models published by previous researchers, the Inversion Net, which is an encoder-decoder network, and also the Velocity GAN, which is a generative adversarial network. And on this table, the values in red represent the best performance for each metric. And our model actually performs considerably to other benchmarks, even outperforming them on more complex velocity data sets. And I want to point out that in the flat vel A and also in the flat fault A, you see that the inversion net and the velocity GAN results have a better performance compared to our model on all metrics. And a potential explanation for this is in the framework of our model that denoises the velocity gradually, making it struggle with prediction at the boundaries of the flat layer. However, this gives our model a better generalization capability, which can be seen in the more complex data sets where our model outperforms all the benchmarks. To qualitatively evaluate the performance of our model, we select a single sample randomly from the test sets, and the result is shown here. On the left is the velocity family, while on the right is the fault family. And on first glance, compared to the ground truth on the far left, our model on the far right does a decent job on all data sets. However, I want to point out the impact of the denoising procedure, which becomes evident as the final prediction of our model is blurry when you compare it with the other models. But it actually effectively depicts the structure and accurately predicts the velocity contrast, also consistently capturing the thickness of the layers and relative velocity. And also for more complex data sets, the curve velocity A and B, and also the curve fault A and B, you see that our model actually mimics or reflects the ground truth better compared to the inversion net and the velocity can. And based on the fact that our model actually outperforms other models in these complex data sets, our model can actually serve as a more suitable prior for classical inversion, which will aid in the convergence of the optimization and also reduce the computational time required for convergence. Also, I want to point out that further work is required to test my workflow on field data and also investigate strategies that could increase the resolution of my model. It is important to also note that these data sets that was used to train my model is synthetic and might also contain some unrealistic geological configuration. However, I have shown that my workflow actually can result in an improved prediction of subsurface velocity from seismic amplitude. Thank you very much for listening, and if you have further questions, please send me an email.